Hello, everyone. So, in this lecture, we will do a brief review of demand paging and we'll look into few page replacement algorithms, basically the techniques which operating system uses to select physical pages that needs to be replaced. So, the reading assignments for this lecture would be chapter 8 and 9 from Dinosaur book or 21 and 22 from Comet book. So let's do a quick review of virtual memory and virtual addresses. So virtual memory, it allows a process to run with only some of its virtual address space loaded into main memory. That means uh, virtual memory allows a process to run even when few of its pages are not loaded into the physical memory. The idea which makes it possible is the virtual address. So virtual address, which actually is what process sees, can be translated to either a physical memory or to a disk. And the reason why we can do this is because of the page tables and memory translation unit that we have. So operating system can mediate the translation of virtual addresses to physical addresses that makes it possible to provide this illusion of virtual memory to the to processes. And the reason why we want to do this is we want to have a uniform view of memory for all the processes, right? And this way, a process can need not worry about memory pressure of the system while it's running. It can imagine, it can think that it has access to entire memory space and do its execution rather than worrying about the memory pressure on the system. So virtual memory is implemented by using demand paging. Demand paging is a technique where the pages are brought into main memory when they are absolutely needed. That means pages are like we will assign physical page to a virtual page or to a virtual memory only when it is absolutely needed. And the process of bringing the page from the disk to the main memory is called swapping. So we usually take the page that is already in the main memory back to the disk, and then take the required page from the disk and put it back to that particular physical page that we just evicted, or like we just swapped out. Okay. So the process of taking the page into the disk is called swapping out. Similarly, getting the page from the disk into the main memory is called swapping in. So how does demand paging works? So as we know, a program can run without all its pages in the main memory, right? A program can run just with some of its pages in the main memory. So what happens when a process tries to reference an address for which there is no physical memory? That means for which the page table entry, for which there is no um, page in the corresponding physical memory. What happens then? So here, hardware and software needs to cooperate to make things work. So the way this happens is we extend page table entries with a present bit, with a bit that says whether that particular virtual page has associated physical page or not. Okay. If that bit is set, everything goes fine. However, when the bit is not set, a page fault occurs. Basically, a trap happens to the operating system, and operating system gets an opportunity to bring the page from the disk into the main memory and set the corresponding present bit in the page table entry. Okay, and yeah, this is enabled by the present bit, which is the least significant bit in the page table entry. So this is an example of x86 page table entry where you can see present bit at the end. Similarly, different architectures also have this present bit in their page table entries. So what happens more concretely on page fault? So when a page fault occurs, first operating system needs to find a physical page that needs to be replaced. First needs to find a slot in the physical memory. Okay. And that slot could be either already used by some other process, or it may not be used by other process. Okay. If the if that particular physical page is already used by some other process, then it needs to see if that physical page has been written to, or if it is dirty, then it needs to save the physical page back to the disk. Like if the page is not modified, then you don't need to save it back to the disk, right? We can just discard the page because the copy is already on the disk. So we can just discard the page. However, if the page is written, then we need to save the page back to the disk. Okay. And once we select the physical page, we need to, once we save the contents of the selected physical page onto the disk, we need to select the page that we want to bring back in. And then we should load the selected, we should load the target page from the disk into the selected physical page. And then we update the corresponding page table entry by the by updating the present bit, and then we restart the faulting instruction. Basically, we restart the instruction that tries that try to read or write to this address. So that's in simple words how page fault works. And in order to support this, operating system should maintain a list of physical pages that are free. And also it should maintain a list of physical pages. And for each physical page, it should also know which to which processes these physical pages are assigned. Okay. The reason why it needs to maintain this is when a physical page is evicted, it should also go to the corresponding page table entries and clear the present bit. So that's why it should maintain this data structures. And as we have seen in the previous week, in the last week, there is this amazing data structure called inverted page table, where we actually store the physical page as the key, and the values will be all the virtual addresses to which that physical page corresponds to. So we can use a similar data structure to maintain this. So, and a brief distinction between virtual address and virtual memory. So virtual address is what a process sees, and it is supported by the operating system by using dynamic memory relocation. Okay. So this is supported by using the amazing memory management unit that we have, which actually does the translation of virtual address to physical address. Okay. And virtual memory is what virtual address sees. And virtual memory, unlike physical memory, virtual memory for all processes, you get fixed amount of virtual memory. Okay. And this is enabled, like this is achieved by the operating system by using dynamic memory relocation and also swapping. Okay. The swapping, like by using the disk, right? So operating system brings back the pages from the disk into the memory and saves the pages that are not used from the main memory onto the disk. So this is the demand paging. So demand paging and dynamic memory relocation allows virtual memory. Virtual address is allowed because of dynamic memory relocation. Okay. Note that we can have virtual addresses without dynamic memory relocation. Okay. However, we cannot have virtual memory without virtual addresses. So what does VM subsystem or virtual machine subsystem has to do to take care of virtual memory? So first, it should, especially when it concerns to demand paging, first it should select the page that it needs to replace. Okay, this is called page selection. Okay, and then, so actually first it should know when to replace the pages, like when to load the pages, whether the pages should be loaded before the process runs or while the process runs, or can process tell me what pages to load. So it needs to know when to load the pages. Okay, that is page selection. And the second thing that it should worry about is page replacement. That means once it knows when to bring the pages into the main memory, it should also know which pages, or like where in the physical memory that these pages should be loaded. Okay. These are the two decisions that virtual memory subsystem should take. Okay, page selection, where it should know when to bring the pages. Page replacement, that means which pages to replace, which pages to throw out, and when they should be thrown out. So what are the possible choices of page selection? Okay, so the default choice, as we briefly saw in like previous lecture, is we can bring all the pages at once. We don't need to worry about demand paging at all. We can do pre-paging. That means when the process runs, or like when we actually get a dot out, we just load the entire virtual addresses. Like we just load the entire, all the physical memory. We just load all the pages that are needed by the process ever into the physical memory, right? So this is called pre-paging. However, this is hard to do efficiently because, as we have seen, we may actually bring unnecessary pages. That means the pages which may not be used by the process, we may bring those pages also. So this is inefficient. Although this technique is used in Windows 10, actually, the way it works is Windows 10 operating system keeps tracks of pages that are immediately loaded by the process when it runs. Okay, so once it figures out that okay, there are certain set of pages that process always needs when it starts. Okay, once it knows that, then it maintains the list of those pages. So before the process starts, it only brings those set of most frequently used pages. So this is called prefetching. And for each program, Windows 10 actually maintains a file called prefetch cache. It usually ends with pf. If you have seen some files on in your C drive with ends with pf, those are prefetch cache files. That means for each program, Windows knows which pages are needed for the process to immediately start running. Okay, so instead of loading each page on demand, it just brings certain set of pages at once, and then lets the process runs. Okay, this is called pre-paging. However, it's very inefficient, right? If you bring all the pages, the process may not use those pages. The other approach is request paging. Here we can give the responsibility to the program, so that program can tell us which pages are needed by it. Okay, so before the program runs, program will tell the operating system which pages in its virtual addresses are needed by the program. That way, operating system can only allocate pages to those virtual addresses, and it can keep the other pages empty, or like it need not allocate physical pages for other virtual addresses or virtual pages. However, this is very hard to do in practice because it's hard to predict which virtual addresses will be needed by the process before before running, right? Because most of the execution depends on the user input, so you cannot predict user input. So it's hard to get this thing right. The other most popular approach, as we saw, is demand paging. Here, we just run the process without loading any pages, and we only load the pages when the page is actually needed by the process. Okay, and almost all the paging systems, in most of the almost all the operating systems, they use demand paging. However, in Windows 10, it uses a combination of pre-paging and demand paging. So it brings certain set of pages before, that is pre-paging, and when the process is running, it uses demand paging. So, but all the operating systems have demand paging as one of their components, definitely. So once we know when to bring the page, the another decision that dynamic paging technique should take is which page to replace. So we have seen like we have seen the page replacement, like we have seen dynamic paging selects a physical page to replace, right? Or selects a physical page where it should bring back the page from disk. So how does VM subsystem selects this page? So before getting into details of what techniques we can use to select the page, let's see what happens when the operating system is running at memory capacity. That means imagine operating system is running with all the physical memory in use. That means there are no free pages in the physical memory. Like the usage of the RAM is 100%. Okay. Here, every dynamic paging request needs an eviction because entire physical memory is being used. So any page, in order to bring any page in, we should uh, swap out one of the physical pages that's already used because all the physical memory is being used. So the goal of page replacement algorithm or like page replacement technique is to select such a page such that that page is least useful, or rather that page is rarely used by the process to which it is assigned to. But as you can imagine, it's a huge challenge, right? How can you know which page will be used least by a running process? You cannot know it. So that's why page replacement in general is a very difficult problem, because you don't know. It's very hard to know which pages will be used by a process, right? And furthermore, there are many challenges in creating a good page replacement algorithm, or in general, like the holy grail of page replacement algorithm is to find a page that is least useful. Okay, so once we find a page that is least useful, then we can always do the swapping in and swapping out. So the fundamental problem is to figuring out the page that is least useful. Why is it hard? We don't know the future. We don't know when the process might need some page, right, in future. However, we can use the same technique that we used in processes, where we can predict the future behavior by using its past behavior. Similar to least like LRU policy, where we can kick out pages which are least recently used. Okay, basically, if we can keep track of pages that are used by every process, then the pages that are least recently used could be potential choices, like could be the pages that are least useful. Okay. However, even figuring out least recently used pages is also hard, because we need to keep track of every memory access that the process is making. This is this is very hard to do it in practice, because where do you do it? We cannot do it in software because process is running. You can do it in hardware, but in that case, we need to trap for every memory access, right? As we know, memory accesses happens through MMU. So unless MMU lets us hook into every memory access, it's hard to keep track of memory accesses that are made by a process. And furthermore, finding the least useful page should be efficient. Okay, so we should not spend too much time trying to find least useful page. So we should have less overhead. And the most, like the common approach is to get imperfect information about the usage of a page, and at the same time ensuring that we are efficient in figuring out least useful page. Basically, strike a balance between accuracy of our findings versus speed with which we can do the page replacement, or like speed which we can select least useful page. Okay, so we in general, what happens is we usually track information imperfectly. Okay, and then we use an efficient way to select uh, the least useful page, because since we will be using the inefficient, like imperfect information, most of the times the page that we select may not be the page that is least useful. However, on a long run, this kind of works out well, because this provides a good balance between efficiency and accuracy. Okay, so in the next part, we will look into various page replacement policies. Thank you.